Locate absolute extrema. Alright, next thing we need to talk about is locating absolute extrema algebraically. We've already talked about locating relative or local extrema algebraically using the first derivative test, which again, first derivative test said that we need to find the critical points, and then we needed to compare the derivatives to see whether or not the derivatives changed from positive to negative or negative to positive. And again, that's how we found local extrema. But how do we find absolute extrema algebraically? Well, first let's look at what we know about absolute extrema. So where do absolute extrema live on a graph? Well, by looking at absolute extrema, we can say they live at three particular points. And we can identify those three particular, maybe points is the wrong word, but three different categories of points. Now, if we look at this first graph, we can see that we have an absolute minimum at x equals 2, and we have an absolute maximum at x equals 4. And as it turns out, x equals 4 is an endpoint for our closed interval. So when we have a closed interval, we know that endpoints can also be absolute extrema. Then looking at these other two graphs, there is no absolute max on this second graph, but there is an absolute minimum right here at a turning point. And in our final graph, we can see that we have an absolute maximum. There is no absolute min, but this absolute maximum happens at a corner or a cusp. And we know that turning points and corners and cusps happen at critical points. So therefore, we can say that absolute extrema have to exist at endpoints on closed intervals and have to exist at critical points. So using those two pieces of information, we can find absolute extrema algebraically. But how do we do that? Well, first thing we have to do is we have to find all of our critical points. And we can find the critical points by taking the derivative, setting it equal to 0, or determining when it is undefined. After we find our critical points, we have to find our endpoints, because as we just demonstrated, absolute extrema exists at endpoints as well as critical points. Then we can plug our critical points and our endpoints back into the original function so that we can find what their y value is. And the reason the y value matters is because, remember, we're talking about absolute maxes and mins, which means we're talking about the highest y value only and the lowest y value only. So, if when we plug these critical points and endpoints into our original function and we get the highest y value, that has to be a max. However, if we get the lowest y value, that's going to have to be a minimum. Because again, absolute maximums happen at the highest y value, and absolute minimums happen at the lowest y value. Alright, so how do we find absolute extrema algebraically? So we know that we have to go through the steps, but why do we actually have to go through those steps? Why can't we use the first derivative test for finding absolute extrema? And you don't really need to copy anything down on this page, which is why I made it all available. I just wanted to go through some of the reasoning behind this so that we can keep it in our mind. So again, why can't we use the first derivative test for finding the absolute extrema? Well, absolute extrema exist where we have the highest or the lowest y value of the function. The only thing the first derivative test tells us is it tells us the behavior around our critical points. It tells us if we're increasing or decreasing, or if we change from decreasing to increasing. That's all the first derivative test tells us. It's a description of the behavior. It doesn't tell us what we need to know. It doesn't tell us what our y values are at those critical points. So since the first derivative test does not tell us anything about the actual heights of the functions, we can't use it to identify the absolute extrema because absolute extrema exist at the highest and the lowest y values. So let's take a look at some examples. So our first example asks us to find the absolute extrema for f of x equals 2x squared plus x plus 2 over the closed interval -1 to 3. All right, so let's see here. We can see here that we have a closed interval, and then we can see that our function is a polynomial, which means that it is continuous. So since we have a continuous function on a closed interval, the extreme value theorem comes into play. And the extreme value theorem guarantees us to have both an absolute, not mat, an absolute max and an absolute minimum. So we know what we're looking for here. We know that we have to find an absolute max and an absolute min. So first thing we should do is we should find our critical points. And I will label that CP for a critical point. And to find the critical points, we first need to find the derivative. And the derivative of this function is 4x plus 1. Then if we remember to find the critical points, we need to set the denominator, or excuse me, we need to set the derivative equal to 0 and figure out when it's undefined. Since 4x plus 1 is a polynomial, it's defined everywhere, so we just have to see when it is equal to 0. And that means we can find out that x equals -1/4 is our one and only critical point. Next step was to identify our endpoints. So EP for endpoints. And we can see here that our endpoints are going to be x equals -1 and x equals 3. Then from here, we need to plug these critical points and our endpoints into our original function. So to help us do that, I'm going to draw this t-table. And again, we want our x values to be -1/4, -1, and 3. And these x values are getting plugged in to our original function. So when I plug in -1/4, I'm going to get 1.875. When I plug in -1, I'm going to get +3. When I plug in 3, I'm going to get 23. So now I just need to figure out which one of these is the absolute max and absolute min. Because remember, the extreme value theorem guarantees we have both. Well, we can see that our smallest y value is 1.875. So therefore, there's going to be an absolute minimum at the point -1/4, comma 1.875. Because 875 is the smallest y value, or the lowest y value. We can see the highest y value is 23. So that means that there is an absolute max at the point 3, comma 23. And there we go. We have found both of the absolute extrema guaranteed by the extreme value theorem. Alright, then our next example, we want to find the absolute extrema for the function 25x over x squared plus 16 over the interval 0 to 40. Alright, so we can see here that we do have a closed interval. So therefore, half of our conditions for the extreme value theorem is true. Now we just need to see whether or not if it's continuous on this particular interval. So to do that, we'll take the denominator and we'll set it equal to 0. And we can solve for x, so we'll get x squared equals -16. X is going to be plus or minus 4i. Well, unfortunately, 4i is an imaginary number, which means it's not part of real number calculus, which means that the denominator will never equal 0, which means that this particular function is continuous everywhere, which means we have satisfied our extreme value theorem, which means we are guaranteed to have both an absolute max and absolute min, just like the previous example. Alright, so first thing we need to do is we need to find our critical points. So to do that, we have to take the derivative, and oh crud, we have to use the quotient rule, because it's 25 divided by x squared plus 16. So the quotient rule is 25 times x squared plus 16 minus 25x times 2x all over x squared plus 16 quantity squared. Alright, now we already know that our denominator, or that our derivative, will never be undefined, because we already determined that it'd be undefined at an imaginary number. Which means we just have to figure out when it's equal to 0. So we're going to figure out when 25 times x squared plus 16 minus 25x times 2x all over x squared plus 16 squared is equal to 0. Now, when is a fraction equal to 0? Well, a fraction is equal to 0 when the numerator equals to 0. So that's going to be 0 is equal to 25 times x squared plus 16 minus 25x times 2x. Alright, which we can simplify down to be 25x squared plus 400 minus 50x squared, which we can simplify down to be 400 minus 25x squared. And now we just need to solve for x, so I'll add 25x squared to both sides, divide both sides by 25 to get x squared equals 16. So therefore x is going to be plus or minus positive 4. And those are our two critical points. Then we just need to find our endpoints. And as we can see, our endpoints are going to be x equals 0 and x equals 40. Alright, I've run out of room, so let's just get rid of this stuff. Shrink that down. Zoop. Alright, then we just need to take our table and substitute in our values. So we said our critical points were -4, +4, and our endpoints were 0 and 40. When I plug these into our original function, I'm going to get -25/8, +25/8, 0, and 125 all over 202. Now, since the extreme value theorem does apply here, we know that we are guaranteed a absolute max and an absolute minimum value, which means we just need to find the largest y value and the smallest y value. We can see that the largest y value is 25/8, so we're going to have an absolute max at 4, 25/8. And then our smallest y value is -25/8, which means that we'll have an absolute minimum at -4, -25/8. And there you go. We have just found both of the absolute extrema guaranteed by the extreme value theorem. Alright, so let's just do a kind of quick review about what we know about absolute/global extrema. So since we're talking about absolutes, we know that these have to exist at the highest or the lowest y value of a function. Based on things that we've demonstrated, functions can have both absolute extrema, it can have one of the extrema, or it can have no absolute extrema. However, if a function happens to be continuous and on a closed interval, that means we are guaranteed to have both absolute extrema per the extreme value theorem. So, when we are looking for absolute extrema, we need to check the y values of the critical points and the endpoints using a function table to find our absolute extrema. And then finally, let's do a quick review of extrema. Our two types of extrema are local and absolute. In order to find the local extrema, we need critical numbers and the first derivative test. To find absolute extrema, we need critical numbers and points if our f of x is bounded or on a closed interval, and a function table. Now, the million-dollar question here is, why do we even care about absolute extrema? Like, what does this even matter to any of us? Well, there are often situations where we have a function and we need to find the maximum or a minimum value, such as if we were looking to maximize the profit of our company. We would want the absolute max there, and if we have our profit or our revenue function, we can do just that from the function and figure out what our maximum profit will be. Another example is if we are a construction company or a manufacturing company, what's the minimum, or how do we minimize the amount of material used to manufacture a product? So if we had a function that modeled our amount of material, we could use that function to find the minimum amount of material we'll need to produce it. Or if we were launching a rocket on a certain amount of fuel or with a certain amount of weight or payload, we could use the trajectory of the rocket to figure out what the absolute or the maximum height would be of that rocket, and would that height be high enough for us to do whatever we needed to do. Alright folks, that is it for locating absolute extrema.